Okay, so welcome everyone, and welcome to this new stream of Eaglefly, the experimental debugger, where we are on an adventure to understand the IA32 architecture and the 64 Intel architecture. And we've been going through a long track of episodes that we've been searching for concepts inside the architecture itself and understanding the architecture so that we can see and understand what's going on inside the process every time, uh, each instruction at a time. And so I think that um, today we will continue doing that. And yeah, okay, so please, I would say that if you have any questions, leave them after the stream has ended so I can watch them and answer them. You can post them on Twitch or Twitter or YouTube, and I will happy to answer them. With that in place, let's open the Intel IA32 architecture manual that I have already opened, and let's see where we left off. Sorry. Now, the top of the stack, I mean, that means that it's the top. It's the last one that gets pushed, isn't it? So does that mean nothing gets pushed after that? Which doesn't make sense because we had it here, isn't it? That, I mean, if it was here, all this stuff should be after it, you know? Unless we didn't do it right, and probably we have to check it back. But let's see. So assuming this is in the top of the stack, okay, return instruction. So yeah, I mean, because it's pushed afterwards, it's gonna be first to be popped the IIP register, and later on you can put, well, the return instruction pointer into the IIP register, and later you have the segment selector for the code segment, and it put it into CS register. Okay, this is an image of how we do it. This is stacked during the near call. So as we can see from this, is that basically the processor doesn't care. The processor doesn't care at all about which process is running, you know? I mean, it can be running one process and then running another process. I mean, a procedure in another process, and then returning from that process. I mean, and all it's going and happening in the stack, you know? Like, like you call me, I do it, man. You call me, I do it. So it's like, you know, I mean, super straightforward. I mean, it's like he doesn't care at all. He just give me something to process and I will process it. And that's kind of cool, isn't it? I mean, you don't have any this kind of garbage thing. Well, and of course, I mean, probably there are certain reasons why to protect against that kind of stuff if you are doing high level stuff. You know, when you divide processing into different memory spaces with protection levels and stuff like that, and so that they cannot inject code or have any potential uh, craziness going on. But you know, I mean, talking about processor concerns, he doesn't care at all, and that's really neat. And another cool stuff is that, hey, we, I mean, no, I mean, before this, I assumed that I mean, I didn't know that, for example, that you could permit not to. Uh, I mean, you can control, since you can control the stack pointer, you can rather erase the whole parameter stack, or you can leave them if you want. They will be there, you know. And I mean, it depends. It has certain, probably has caveats, but I mean, for example, you wanna permit to leave all the data in there without popping. You know, if there's a reason to it, you can leave it there, and it's never gonna be get back. You know, and that's kind of funny, because I think, let me think about it. Imagine that we are inspecting our process, you know, and oh, just where is it? Let me close. Oh my god. Oh my god. Yeah. So imagine that we are right here. I don't know. Probably we can go directly to. Well, we can run it, I guess. And you know, I mean, for example, we are here on create process debug event, yeah, and we're gonna call this, or you know, I mean, we're here in a stack, isn't it? And you know, this is like in a stack. This is a frame stack, you know, and this is gonna be popped once we left off the braces, you know. So they're like this kind of. Even though there's no procedure inside here, there is like this kind of concept of stacked frame frame bases and frame stack frames happening across the code. So if I'm inspecting on a buffer, I can look into buffer and see, hey, this is the thing that we get. And if I'm inspecting, but once I enter this, I don't know, I don't have it, but we could, if we if we modify the stack frame and say, hey, don't erase the whole stack, keep it right there, and oh, don't erase, yeah, don't erase the stack, keep it the parameters as there, and I think we should be able to look at them, you know. And we just, although I mean, probably there's a reason not to do that. I mean, if we don't, I mean, another way is to cache them into memory, you know, and I think that's a little bit more, yeah, it's a little bit more sane, because keeping them on the stack, probably it's not such a good idea, I guess, because of the way that the process is running onto. I mean, we don't want to keep it there, you know. This is gonna be bananas or something. We have bytes written there, and now we don't have bytes written at all, isn't it? So if you can see, I mean, when working on code, the stepping to goes per instruction, well, or yeah, something like that. I mean, per set of instructions, per set of expressions instead of instructions. So it jumps through a whole set of instructions in once, you know. which is kind of I mean, it's hard to know what's the right thing to do there, because I mean, we could see the whole thing here, I mean, if I go and say, hey, show me this assembly, and we know that this assembly is gonna have a lot of stuff in there, like it depends on the instruction or the set of instructions that we are doing. It's gonna be like, hey, please move on to registers, move on to memory, make these operations, call Win32 get handled from ID, which is some of the next instructions too. There you go. Whoa, where am I? There you go. Here is changing per instruction, here is changing per oh, I know why. That was a jump because of branch prediction. I mean, not branch prediction, but because of branch correction, I think, where you move from one place of the code base to another part of the code base based on what it found there. We have here something on the stack. And all these pertain to that. Continue debug event. I don't see. So yeah, we are using RAX to gather all these data here. And here's a call. There's a call. And there you go, we got it. So this is and hey, this is a far call. If you see, this is a far call because that's not a thing that's inside a process. So it needed to go to another process and hey, tell me what's going on there. Or probably, I don't know if they are loaded into it. Probably they are loaded into it because it's loaded statically, isn't it? So yeah, I think all this is statically loaded. So it was a near call. Yeah. RCX RSP security check cookie, whatever, and it's gonna pop in on the stack from the RDI and pop in RSI. Yeah, I would like to see this stack, I mean, like in a good thing, Okay, now we jump back. I don't know where am I right here, but we return. So we return to the place where we are in win main, because remember that we are in an offset here. And the last thing we did was to call debug day tracer. Here's the call, and here's the let me move this. So we have the call that we were doing right now, and then we got a way to get back into the place where we left off. And if we see, I'll see if we, in the registers we have it, should be RSI and RDI, no, RSP and RBP. Where is it? Here you go. We have RSP and RBP. RBP is 0 because it's a next step frame. RSP, Control C. Alright, so yeah, I was like, well, thinking, yeah, we are here. I mean, we can continue doing all this stuff. The registers that are gonna be changing. And now we are here. Okay, let me see what's going on here. We are in debug rate renderer, and we're gonna move from the stack pointer to RDX. And I don't know if this one is the one that's gonna go, because RSP plus 120. I don't think we have another function there. No. Why do we have two calls there? Let me see. If we jump it, no. Let me go back into here because I want to see it back. That's here. Okay. Right there. Right there. Now I want to enter. Now I'm on Eaglefly.cpp. So this is not useful right now. Where is the other? Here is. Oh my god. This is crazy, Mr. Vicious. It's totally crazy, all this stuff. Okay. Let me see. We are in here, I believe. There you go. And we're looking at pointer RSP. Okay, stack pointer. And moving up on the stack pointer. And this is the entry point. We're pushing this stack in RDI. So this is all preparation for the stack, isn't it? We are pushing, we're moving something from the RDX and RCX onto memory, and then we're pushing the stack, and then we are it's a constant value to the RSP. It's a subtract, so it's gonna subtract the RSP. That's gonna be moving down the stack. That's good. That's what we want. And then, oh, there you go. So when we move on the stack, that was ready to move on. And then the stack pointer, it's I don't know, 472 bytes downwards. Okay. And now we have memory. Okay, memory, the pointer. we have memory pointer, move it to rex. So let me see here. We have rex here. We have debug state. We're offsetting +8 because debug storage is 8 bytes. If I do remember, let me go into platform so we can take a look of that. So yeah, because memory index is gonna be 8 bytes and debug storage is an offset but 8 bytes. So basically rex +8 is gonna get you to debug storage, and now we move that to rex. Now basically that can be moved. I mean, we could do this. We could do this in one instruction, isn't it? But yeah, this is not the best thing. We're not optimizing here, so it's okay. Now we're moving rex onto the pointer to debug state, which is what we want in memory. There you go. And that was all. These 3 instructions was that. Okay, that's neat. We got it. And then we're gonna move debug state to rex back again, because why not? Man, it's totally inefficient, but you know, it doesn't matter. And something like, well, okay, I don't know if it would be easier to read if it was more concise, but that's the way it goes. I mean, super straightforward, I guess. Yeah. So I'm moving here and I say, hey, move me back on the debug state, put me on rex. So it's gonna be the same, it's not gonna change because he hasn't done anything with a rex, so it actually has it right there. I mean, if you think about it, we haven't moved rex, so rex is still there. So it wasn't necessary at all. And the crazy stuff is that probably we can modify rex on the fly. Can we modify rex on the fly? Yes, we can. Okay. And that's crazy. Modifying registers on the fly. It's something to think about. Okay, so whatever. So now we have rex plus 80 plus 48. It's where its initialized is. And we are gonna compare. It's gonna be compare. It's a simple compare from the word that it's initialized. It's a door compare door pointer rex 30 to 0. And I know what this is gonna do. If it's equal to 0, it's not here, it's in another, it's in here. EFL, eflex. This is a EFL. Yeah, it's in the eflex. I don't remember where, but it was there. So it's in the eflex thing, which is fine. And now we are gonna jump to So basically these two instructions are like related, you know, because the compare sets us an if flag stay flag bit, you know, somewhere here for the compare, and then the jump no equal is gonna look at that and say, hey, if it's not equal, jump. If it's if it's, so I guess it's gonna jump, and we can take a look here to the address. I don't know if we can. Yeah, so let's see. Boom, we have a clear screen, and we can have a watch here. Let me put it here. I'm gonna copy this. So basically the place where we want to go to jump, and now because there's no equal, XMM 0. Okay, this went bananas. Well, no, it's not going bananas. It's using SIMD registers, XMM registers, and it's going to move something there. I can watch it on registers. I don't have the registers there, no. Where are the segments? Here are the segments. Where are the floating points? I need the floating points. Registers. I need the flag, effective address. This is effective address, okay? Let me go to effective. Is this effective address? Yeah. So the effective address is that and also I want MMX and SSC. Well, I need MMX right now. I need SSC. XMM 0, XMM 1, XMM 2. So first of all, I'm gonna proceed. It's gonna have something to XMM 0, which is basically real. Oh, okay. So he thought that it was convenient to do the floating point thing on the XMM 0 registers. That's why we are seeing that kind of craziness. I thought it was gonna do it on the FPU, but it was not. It's gonna basically load the same value. Well, actually, real 399. This value is probably 0.2, and this is 0.9, 0.6, sorry. Oh no, this is 0.2. I don't know how to read this. But okay, so I mean it's loading the floating point values, doesn't matter. And then it's gonna, and I don't know why they are indented that way. You know, it kind of sucks. I mean, looking at this assembly, it kind of sucks. You know, because it's super bad indented. It's not, it doesn't have any kind of order. It kind of sucks. let me see here. It's gonna move the frame buffer to the RCX, so we can look at RCX. Oh Jesus, and you move me back, oh my god. And frame buffer it's 0. Oh no, here you got it. And now we can clear screen. It's a call. Can we step into? Boom. And we go to another part. It's on the same segment. The nice thing is that he has this kind of thing, but you know, it should have more, you know. It's not just this, you know. I mean, yeah, we know that this is Eaglefly CPP. I mean, is there a way, like, I mean, it's good to have the code itself, because we know that we are moving through here in a really nice, I mean, if you don't understand assembly, it's good to have the source code, like blah 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 blah. But I think, I mean the the assembly itself can't tell you everything if it's good organized, you know. I mean, I know, like, I have no idea. I mean, probably we can, like, segment or put, like, oh, this, for example, if we do this, like, hey, this block of instructions relate to this thing, you know, and it's like, oh, okay, now I know what's going on, you know, or something. Or this block of instructions will relate to this expression, and these blocks relate to this expression, or, you know, because you can map them, you know. I mean, you can have a mapper here, like, hey, I'm looking at this expression, or I'm looking at this, or yeah. Move as, store, RSP, BPA, blah 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 blah. F3. Okay, it's gonna move, and this is the same. I mean, if you can see, this should be the same, because it's gonna, this is also SIMD moving up to memory, the registers that he loaded, that we have it already. We loaded onto the registers, and now we are loading up onto memory, because, and the interesting thing, I don't see any pushes here for the stack. This is normalized, it's normalized, it's normalized, clear screen, it's normalized, clear screen, it's normalized. This, we're going to test here if it's equal. We're doing a round right, round real 32 to U32, blah 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 blah. And we have a pointer with where's the instruction, and these are a lot CCs. Okay, F10, these are the parameters, and we're moving up to memory themselves. That's RSP plus 20, RSP plus, well, yeah, it's doing it. I mean, it's moving up, it's adding it to RSP, you know, in the stack in memory, 8, 10, 18, 20, and they are not, oh, this is nice. Okay, so we are moving 8 from RSP, then 10, well, 10 in hex, that's 16, 18 sec hex, and 20 hex. And this is gonna move RCX, that's the frame buffer, yeah, to that place in memory. So they're pushing the parameters into memory, and there is gonna move RSP onto the sum of all of those, I believe. If I make the sum, I could take a look at it. So we can say 8 plus uh, uh, 8 plus 10 plus 18 plus 20. And yeah, I mean probably because they have to be aligned to a boundary, so they move this thing. I mean this RSP, this calculation here was made by the processor itself. Yeah, so they were aligned to a boundary, probably 64. So we have 60. Well, if go 58 is what, 88. 88. 88 is not aligned to 64. Um, yeah, I need to see why it's not aligned there, or why should. I mean, it's gonna be, and probably it's gonna be moving RSP a little bit more all the time, because for example, this blue, there also, there should be there. So it's not moving RSP until later. It's just using the offsets from RSP here. Which makes sense, I guess. Oh, here you go. And this is RSP. So it moved RSP until the last. And that makes sense because that means that you don't have to be moving all the time. But that means that he needed to calculate all this stuff because he didn't know how to. I mean, if you're moving RSP until the last, well, that saves you calculations because you're not moving around. But yeah, it makes sense, I guess. RAX, all these are calculations. And there, this is another code segment. Well, it's the same code segment, but it's, I was just referring to another part of the code, I guess. With another code offset, you know. Okay, it's interesting. We are there. We're gonna call this normalize. We can enter there, and this is the code segment for its normalize. It's gonna do that whole thing, you know. Jump below. It's gonna do jump below commas. And then we are moving up the stack by 1. Here he do it 18H 24. And here is yeah, because it's always moves RSP upwards here, so it and it returns back. And then we have the word pointer result. Oh, okay. So if you see here, it always moves by the same quantity. You see? So he already knows beforehand how much size it's gonna take for the stack to operate on it. And then we have value. This is value. It's gonna move it down maximum 0 because it's a floating point number. And we have commits. I don't remember what does it compare if yeah, this is kind of hard because I mean since they're making this jump. I mean all this is serialized and see and it's done here, But I mean probably they're doing like extra things that's not like necessary because yeah. But it's still there, because you haven't saved the result into memory until here, you know. And EAX we don't have any kind of value, but it's using RSP to have the value itself, because value is greater than equal to 0 and value it's less than equal to 0, so it has to be true, I guess. So if we see EAX is 1, because that's what the thing that an RSP. So he used RSP to make the calculation instead, which is kind of crazy, I guess. But I mean, yeah, because it's moving. Oh, okay, I see. Here you go. It moved 1 or it moved 0 depending on the calculation of the thing. You see? Because since we jump from here, he make this, and then he jump. Absolutely jump. But if he make it on this decision and he has the two jump, okay, I see. Here are the two jump backs, jump below, sorry. And depending on the jump below, it's gonna be it will go to here or to here. If he find a way to get to here, he didn't use the jump belows at all, you know. And he used the jump to jump basically this one, you know. It's funny. It's kind of interesting how those instructions get realized and just you put jumps, you know, jump below this or jump below that, or don't do this, and just realize and continue checking, and jump if something. With I don't think I mean I don't know which is the best way to like organize this code, but at least we are starting to understand it. You know, it's like, hey, this is doing this because yeah, it's gonna do two comparisons. It's gonna do a little bit of moving here. You know, if something happens. I don't know what commits is. I don't know what commits, but we can find it. It's compare if single. It's an XML0, so yeah, it's an instruction that we didn't check out, but it doesn't matter. I mean, we see like the workflow here, you know, and yeah, so it's gonna do all that kind of things, and then he jumps so it doesn't grab this and he grabs this. But this is the important thing: it grabs this or it grabs this. You know, it depends, depending on jump backs and jumps and things. And then it's gonna do that, and then we have the result from EAX, and then we grab it and store it onto memory, and then say, hey, please move that back onto EAX because why not? And then we are gonna add, and I mean, for being sure, I know the order that Visual Studio is doing with the instructions themselves, because for example, this is I mean, now I move it on to EAX, and now I move the okay, let me see, because we still have the result, you know. Of course, it's on the stack, so the stack is gonna be pushed, and we're not gonna get that value anymore. But we're gonna return it, so we have to have it somewhere, and he's gonna use it. He's gonna keep it on the register itself. That was necessary. Okay. I mean, I don't know if another way to think about that is that probably, I mean, instead of copying it to the register, you can copy onto another place in memory that you're not gonna use. Although, I mean, that's not. I don't think the compiler can do that. So he used EAX, some register to keep it there, and then he just move up the stack, the same quantity that he wants, that we push it back downwards, and then return. Okay, and now we are there, and now we're gonna test. Okay, do you see? That's why he used EAX, because in EAX is the result. And now we have a test. We have a commits. Cool. Yes, he used this one since it doesn't have any packed values there, just one. Probably it was better to do that. I don't know. It was crazy. I mean, I don't know. We don't care too much about that. And yeah, so it's gonna do basically the same 4 times. And it's gonna test it if it's yeah, it's gonna be jump equal if it's false, but it's true, so it's gonna do it. So it didn't jump. Now we're gonna move green to x_0. We're gonna call that test AX. It didn't jump, so it was true. It's gonna keep there. We're gonna move. We're gonna call, and we can see x_0, and it's gonna move it to the pointer on our SPA8. So it's gonna be in the stack. The values move on the stack when the call happens. Then the stack gets up 18 bytes. Then we're going to value to x_0. So now the thing that I know, I mean, value in that value was the same, isn't it? Let me go back. Just because, I mean, value refers to that offset, isn't it? I mean, pointer value, it's 1. And x_0 has 1 also. So it's basically the same. So it has like 2 pointers there. I don't know if they refer to the same thing, because I mean, if I go to registers and I go x_0 has 3 effects, and there's a value 1. Oh, I hate this. I hate it. So it didn't change, you see? So yeah. So this is like a 1. I don't know why it does this, but I mean, since it already has here as an offset, why does he have to have this value? Then the compare, the stupid compare, and then jump back, jump below, sorry, jump below, yeah. it's gonna multiply with the XMM0 255F by the blue. We're gonna have, let me put it here on the watch. XMM0 is the only reliable window, I guess. We have that, and now we have the call. There's gonna be another call there. It's gonna do a bunch of stuff. Now I don't see the pointer here. Where's the pointer? It's because we don't have the file there. Okay. It's gonna do another bunch of stuff that's gonna be basically the same. I don't know where is it, but convert from real-32 to U32, convert TS to SI. That's gonna be a conversion to an integer. Yeah, there's some kind of casting there that we do, and then pass it to rex, and then EAX is gonna be moving to, and look, they use EAX here and then pass it to rex, and that's interesting because we just, I mean, rex is 64, EAX is 32, so, and we want to do 32, that's good. And then we move to RSP, and then RSP, I need to have the code. Where is it? I don't have it here. Oh yeah, it's in platform, isn't it? Yeah, here. I mean, it's basically this, you know. I can put it here. I can see, and right now we first asserted that it was value greater or equal to 0. Then we some kind of add 0.5 to the XMM0 register, and I believe it's this craziness here. And I don't know. The value to XMM0 value is that. Okay. Now the result haven't been moved. The result is 1. I don't see result here at all. But this is the casting, and XMM0 has the value. We push it to rex, so we have it there. In EAX we have it. Now we put it to RSP, wherever RSP is pointing to. And hey, this is nice. They use RSP, and now they move it to EAX. Totally nonsense. But hey, look, they use RSP to find the result value. They didn't have anybody. I told you that that was not necessary. They don't need to do this kind of stuff. But hey, you sometimes do it, but whatever. Okay, so this tag was moved by this. It's 18. So I think it's more like I don't know. Well, yeah. And we return. I don't know why it's 18, but we can see. Now it's gonna move. It's gonna do nonsense there, and then the stack is gonna be moved. So he always used registers, and now he have offsets, you know. So he thought, hey, why do he? Oh, I think why, because since you know it was the only value there and it was the top of the value, it's like, hey, I know where the stack pointer is, please copy that to here, please. And then he just moved it back. Cool. And the result has oh yeah, because we do 0xFFF, and this is gonna keep it on EAX, I believe. And then we're gonna move it from EAX back to red 255. Okay, we have it on red 255. Okay, so this is pretty straightforward. Now move it. Now we have it. We have a move there. We're gonna make some shifting lefts, some shift lefts to EAX and shift EAX to 8. So first he started with green, shift left 8, good. And started at EAX. Then blue on ECX, because he knows that he needs EAX already, jet. So we have ECX, and it's gonna make an NOR between ECX EAX. There you go. And I don't know where does he store it. ECX, I guess. Yes, it's in ECX. And now it's gonna move ECX to EAX. There you go. Then it's gonna okay, the red to ECX because it's gonna use it, and then it's gonna shift left 10, that's 16, that's the red 16, I guess. There you go. We have that. Then we make EAX ECX, and then we start it on the EAX. We have it there, good. Then we move it to we move alpha 255 to ECX. We use the same register, and then we have ECX shift 18 hex, that is 24, and then ECX EAX over. We keep it. And now we have the value on EAX. We move it to our color, and there's the store. Okay, that's good. That's pretty neat. and we can continue doing all day, isn't it? How come loops are done? I mean, this is good. Let me see loops. This is a simple loop. I don't think it's gonna be crazy banana. Although it has another offsets and stuff. So let's see. So first of all, we need to get buffer and put it to RAX because it's x64. Okay, F10. Then RX plus 10 guards the data and RAX. And we can put here RAX instead. We got it. And then it's gonna move RAX to test, which is what we want. With a U32 pointer. So this is interesting because this is a quart. Oh, this is a quart. But I say that it's a U32, so it's a thwart. And then this is gonna move it to our RX back, and then row test. RAX to row test. Pretty straightforward. And then this is where on the stack it's gonna move it and set it to 0 to Y. Pretty neat. Super. I mean, all these things should be this way, you know, where you just offset the stuff and stuff like that. Of course, it will be a little bit harder to read, but it doesn't matter. So there you go. All those nonsense was that. This is the Y equals 0. Then jump if equal, I guess. We're gonna move to 07 FFFFF. I don't know where's that. There you go. So it didn't do all this stuff, and all this stuff is RSP plus 20. So why does it jump there? Oh, okay, it's the 4. It's like, why does it do it that way? And the reason is because these things are done when the loop is running, isn't it? Because this is jump greater or equal, and here it's gonna jump back. So it's like a series of jumpings, you know? Jump, 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 jump. Which is crazy, I guess. It should be simpler. So we have buffer, and we're gonna store buffer into REX and then offset it to get height to EAX, and then we're gonna descend high EAX 1, and then we're gonna, okay, that's good, that makes all sense, because EAX was not used anymore because we had it on row test. That's good, have it on row test, and it's on the stack. We got the pointer, we're pointing to there. Where is it? Here is it. It's in row test. So we probably, what's this in 64 didn't care about the cast at all, I guess. Yeah, it doesn't care. I mean, it's still a pointer. It's gonna keep it that way, I guess. Okay, so RAX plus A, EAX decrement, and then we're gonna compare EAX against RSP plus 20. Which is Y. We keep a Y there. And if you think about it, RSP hasn't been incremented here because he doesn't know if he's gonna enter to X at all, you know. That's good. So the last stack value is Y here, and X it's not defined yet. That's good. Okay, now I see how it works. I mean, all that he knows is that all this is in the stack from base on, and ifs, fors, jumps, branching, and all the stuff is not until you have validated the condition. Okay, so now we have F10. We have a compare between AX and that, and we're gonna if greater or equal, yeah, we're gonna jump, but we didn't jump, so we go to the next instruction, and now we have to move row dest to rex again, and then move rex to dest again, and then RSP plus 34, we're gonna set it to 0, and then we're gonna jump to another place, and there you go, and then it's gonna say, hey, okay, so it's gonna move the buffer, and then RX plus 4 with, and then decrement EAX, and then we're gonna compare if EAX is that, and then we're gonna jump if greater or equal. We didn't jump. Then we have a bunch of movements here. It's gonna move this to RX. Our color is gonna be moved to that's at word. Our color is at word. I don't remember. Yeah, it's at word. So it's moving at word to ICX and a quarter to RAX. And then ECX and RX, I'm gonna move ECX to RAX as a pointer, and then I'm gonna move So REX is that. It's a memory pointer. We have a memory pointer, and whatever that pointer is, we're modifying it. It should be this, isn't it? It should be test. And yeah, it is test. Okay, so it was just using REX instead as a pointer, and then we're moving this to REX, but it's the same, so it doesn't matter. And then add REX to 4, because that's the quantity that has to move, because it's the size of the pointer, because it's U32. Okay, then we move core pointer des, we move RX to test, and there you go. And then we jump back to the place where we didn't jump back before, because we were jumping. We jump here from here to here, but this is the cool part, because this is like the little bit of instructions that we don't do every time. We just do it in each loop, and that's crazy. If it was a do, it wouldn't have this jump, for example. So we have move, and the move basically is gonna do, hey, move our speed plus 24h to EAX. That's gonna be 0, because we say that RSP plus 24h is equal to 0. That's basically EX. RSP plus 24h EAX, and then tell me hey, increment EAX, and then do the same stuff. Now it's gonna be EAX to RSP plus 24h, and then it's like instruction. And this is kind of funny, because I mean, here's where we started before, and this is just incremental. And then we can continue with this, you know. We can do the same stuff again. EAX, decrement it by 1, save it on EAX, compare it, decrement, jump, do the jump, and do the same stuff again a bunch of times. It's gonna go crazy, and only when we jump greater equal it's gonna get it to here. Can I set a breakpoint there? There you go. And we will continue. And it's gonna do the same stuff, but now it's gonna do some extra stuff. It's gonna be buffer, keep buffer, then RX plus 4, where is the width, and then row des. It's gonna load it to RCX, because row des is pointer, well, and then RCX plus REX times 4. Okay, it's gonna do, okay, hold me here. REX is gonna have, oh no, it's gonna load load effective address. We're gonna load an effective address. Okay, that was move. that's gonna move load effective address to REX, that's RCX, that is rodes plus let me think about this. Rodes equal rodes plus buffer width. Okay, so yeah, that makes sense, because it has to be RAX, but RAX times the size of rodes, that's a 4 byte, so it has to be RAX times 4 plus RCX, and that's the effective address. And that RAX is gonna be, hey, now write this to rodes back, and then we're gonna jump back and do the same calculation stuff like once again, so it's a loop within a loop, and then add and return F10, load effective address to RAX, we change it and put it on rodes, which is gonna be the same. There you go. We jump back and we do the same stuff back again. Hey, we read assembly. That's good. That's really good. It took us some time to get it, but now we're getting it. You see? We are reading assembly language. That's good. Alright, that's a nice test. We have some for loops, some branching, some calls, returns, jump stacks, return stacks, frame stacks, I don't know, whatever we got into our front, we're gonna get it. And yeah, and I mean, this was like a practical thing because we needed to practice on this. So yeah, man, I don't know if we want to. Well, I think we should continue on this. Let me see what we can do. And thankfully, I mean, this is pretty straightforward. I mean, it doesn't have any optimizations that can struggle the understanding of it, you know. Alright. So after our test on reading assembly for first time, let's continue reading this thing, because now we see that the parameter passing can be done differently. We see in this that it's probably normally done on purpose registers. It can be done on an argument list or on the stack. Oh. and we didn't take a look at TS, which is gonna be something uh, uh, that we probably want to do. Let's check out that, because we can go, well, we should go, I don't know, to call stack right here, I guess. This is, there you go. And now we are right here. Now this, we have CS, and we have we can, I don't think it's gonna call CS because he doesn't need it to, but probably. We have absorbs, a move in there, another move. We have a convert an integer to a real, and we made the subtraction move. There's a subtraction there. Oh no, the subtraction is here, it's below us. Okay, so we have EAX. We move 0. I don't know why. Probably because, oh yeah, it's because we're doing some fancy stuff here. We're moving 0CH. It's 12. And then multiplying that by RAX, and then we're gonna get debug state. I don't know why RAX was that. Oh my god. Okay, we're gonna use RAX, that's going to multiply square to RCX to get to 4EH. Okay, so basically it's gonna get Y advance. Isn't all that crazy stuff to getting Y advance? And it makes sense because it has to first derive it from here and then derive it from here, you know. It's a bunch of offsetting. It's basically fonts, and a fonts, I don't know how much big it is, but it should do it that way. It's gonna do fonts, and REX is gonna be now 0. Oh yeah, because it's 0. Okay. Oh, okay. So it's 3 multiply. Okay, cool. It's a stupid because I mean, well, it depends. It doesn't matter. Okay, so we got REX, it's 0, RCX is debug state, and we have 4EH to get the offset basically for each Y advance, you know, because Y advance is in the 4EH offset, and it's gonna get to XMM and 0, and then it's gonna get debug state back onto REX, and then REX plus 4 what? For that number, I don't know, XMM 0 to that state. Oh, add Y. Okay. It's moving to add Y. There you go. Load effective address, and I don't know what this is. Looks something. or it's gonna load the string. See, it's because of the string, I guess, and it's loading it to array. This is the string itself. This is a string and it's moving to array. Then we have the frame buffer, and we move it to RDX, F9, F10, and then we're going to move debug state to RCX so we can pass it, and then we go to call, and I mean it's not gonna use CS, so it's not like a proper one to test it. But I mean I was like looking at, because the parameters were passed onto registers in this case, but I was like kind of testing different kinds of parameter passing ways. But I think we should do that ourselves, I guess. So yeah, because parameters can be passed between procedures in any of the three ways: registers, argument lists, or on the stack, okay. Okay. So ESP, it stores the values before executing the push instruction. Except the ESP value. Okay, nice.
Okay, that's interesting. We don't need the REX in this case. Okay, so this is specific to 64-bit mode. It makes a difference between for branching and near branching, and between direct branching and indirect branching. But yeah, I mean, first we have to see two Paul gates to understand this thing, because without looking at collocates is kind of tricky. Okay, so we got to the place. Another important part of it, interrupts and exceptions. And let me see. It's gonna take a while to read this, but that's the way it is. But hey, we did. Let me see. Where am I here? Okay. Okay. This is really, really interesting. Okay. The concepts of interrupts and exceptions are this. An interrupt is an asynchronous event that is typically triggered by an I/O device. So it's an event. It has to be asynchronous. Let's write this, shall we? Okay, okay.
Oh, look, here's a breakpoint. This is a number flow int O instruction, bound instruction, invalid O code instruction or reserve O code. Invalid opcode, undefined opcode. Okay, so I think I'm gonna stop here. We did a great job on
rehearsing our assembly language skills. And yeah, well, we have a question that we have to answer right here. Is that I mean, if we see on the code, let me see if I can continue run. There you go. And this is the part where let me move this like this. And right here we are on the exception handler, Microsoft exception handler, dispatching all the events onto our process. So I mean, here we are not looking at any kind of internals, you know. So I mean, we have two kind of perspectives here that we have to match. One is that yeah, we have the possibility. I mean, we know that we have the possibility to make code changes itself to the target process as needed. We know because we've done that before with the CC entry instruction that basically halts execution and it sets a breakpoint into the process itself. So that's clear. Now the thing that we have to see is what kind of exception handling process does Windows execute in this case. We probably I mean probably is that the thing that it does is probably more like this, where the processor itself it's gonna set an interrupt, and it's gonna call the Microsoft's exception handler. It's gonna pass the interrupt. It's gonna do this interrupt. It's gonna pass all the segments back into the stack of the Windows procedure exception handler. That's gonna be somewhere running, and the exception handler is gonna pass the data up to us. Of course, it's not gonna pass this to us. Well, probably with the get context, with get for the context. Probably that's the thing that we pass, and that's the thing that we get from Windows itself, you know. So it's like this kind of transfer process. I mean, we have an intermediary here. I mean, we cannot do it ourselves. I don't know if we can do it ourselves, but I mean, right now what we do is we have an intermediary that's the Windows exception handler and all the kernel stuff, that basically connects us with the target procedure. And I think that's fine. I don't see the problem with that, and especially because that's the way Windows works. I mean, we cannot do anything with that, I guess. So yeah. Okay. So please, if you have any questions of what we did today, feel free to ask them, and ask them please on YouTube, Twitch, or Twitter, and I'll be checking there to answer any question that you have. As for now, I think that will be all, and I will see you all on the next stream.